Okay, good morning or good afternoon. Today, I'd like to introduce you about the electronic circuits 1 course. Okay, in this lecture, in this course, we will have 8 chapter, namely semiconductor diode. Sorry. Okay, semiconductor diode, and then diode applications, typical junction transistor, BGT, DC biasing for BGT, and then AC analysis for BGT, FET, DC biasing FET, and FET AC analysis. So there is a chapter in electronic circuit. So today we will start with introductions. What is the modern electronics era? You can see in the first picture that the modern electronics era is in 1947 when the Bell Labs, Brattain and Berden invent the bipolar transistor, and then the first germanium bipolar transistor is invent in that lab. So after 1947, and the electronics become a major development in the world. So we can see that roughly 50 years later, the electronics account for 10% or $4 trillion of the world GDP. So this is the electronics milestones. We start with 1947, and then until 2000s, and then we can highlight some milestone. This is the integrated circuit in 1958, and then first commercial IC in 1968, and then first commercial 1 kilobyte memory in 1978, and megabit memory chip in 1984. Okay, the electronic device start from vacuum tubes. You can see in the picture A, and then after vacuum tube, it's become the discrete transistor, and then after discrete transistor, we see or the inventor last year in last 10 50 or 40 years ago, they integrate the discrete transistor into SSI or MSI in integrated circuit. SSI is mean that small scale integrated, and MSI is medium scale integrated. And then after some years, they introduce a VLSI, very large scale integrated. So this is the very large scale integrated. So this is surface mount circuits. It means that many components is integrated in one die, like this one IC. So we can see maybe a million discrete component or million devices integrated in one IC. Maybe you can see if you open your handphone or your laptop, you find many IC component in that device. So this is the IC. So this is the numerical proliferations. Okay, this is the commandment. The very popular commandment is Moore's law from the first commandment here. But sorry. Okay, in Moore's law, the number of transistors on chip doubles annually, and then okay, this another another commandments. I didn't explain that bit, explain more. So the Moore predict that the number of transistors that can be integrated on a die will grow exponentially with time. So it means that from 1988, the first IEC, until now, so the number of transistor in some die is mean that you can see this is the die. This is the die, like this one, and the die is 1 millimeter. 1 millimeter. The size is 1 millimeter cross 1 millimeter. This is the one die. So it means that you can see from here in this graphic from 1988 to 2010. So this is the kilobit capacity per chip. So it is increased exponential. It is increased by time to time, and also, so this is the memory IC bits per chip, and then we can see that this is if you see the right line like this one, this is the size of the this is the size of transistor. Okay, this is the size of transistor. So to increase the capacity of the IC, we have to decrease the size of transistor. It means that in transistor we have IC in FET. Transistor, we have two kind of transistor. This is the BJT, or bipolar junction transistor, and FET, or the field effect transistor. This is a two kind of transistor. For example, in FET we have three terminal, namely source, and then gate, and then drain, SGD. And BJT we have the emitter, and then base and collector. This is the terminal in transistor. So what is the size of transistor? In FET, the size of transistor is mean that the gate length. So this one, this is the gate length. This is the gate length. The gate length is the size of transistor. So if you see in this picture, that's 0.07 micrometer. It means that this is the maximum gate length of the transistor. So it's not the actual size of transistor. It means that's not the size from source to drain, but it's only the size of gate length. So this is the size of transistor. And why they only use the gate length to determine the size transistor, I will explain later in the chapter of transistor FET and BJT. Okay, and then this is the number of transistor. It's like a more slow, and then this is a year by year, as you can see that the first one in 1960 to 1970, the number of transistor growth twice per year, and then after this is after 1970 to 2010, from for DRAM memory in blue line is growth twice per 1.5 year, and then for Intel microprocessor here, this is growth twice uh, per 2 years. So after 1970, the growth of the number of transistor in the die will be decreased. Not it's like in the early beginning of the transistor era. Okay, because because you know that the density of transistors become large. So maybe in 2020, the number of transistor maybe not twice per 2 year, or twice per 1.5 year, maybe only twice per year, or maybe twice no, not twice in 3 year or more. So it become the densities become larger. So it's not easy. It's difficult to increase the capacity in the transistor in now. Okay, so this is the Intel CPU evolution. So the development of the CPU is have a close relationship with the transistor, the development of the transistor. You can see that here, the Willamette, the, in the size of transistor in 180 nanometer, and we have 42 million transistor per the die size is 235 millimeters square. And then if the transistor is the size of the transistor is decreased to 130 nanometer, so the number of transistor become large. So this is the 50 millions, and then decrease to 90 nanometer. The number of transistor 125 million in the die size, and the die size is decreased. Okay, so we can see that to increase the number of transistor, we have to decrease the size of transistor. Now if we have the quad core or dual core or silver tone, in the quad core, in the die size of 214 millimeter square, we have 120 million transistor, and you see that the size is 45 nanometer, or 1/3. So we can see that this is the evolution of the transistor. Okay, so this is the rapid increase on density of microelectronics. Okay. So how to design the IC? You see that the first I say that this is the SSI, small scale integrated, MSI, medium scale integrated, and LSI, large scale integrated, and also FVLSI, very large scale integrated. So how to design the IC? So there is if we learn about the IC, so I can define there is a two big big domain of the IC. The first one is digital IC, and then another is analog IC. And analog IC, we can divide into many categories, as like a low frequency and medium frequency, and then high frequency. Okay, so the first we will talk about the digital IC. So how to design the digital IC? The first one, we have to make we have to know what is the purpose of the IC design, and then we have to we have to make a coding of the design IC by using the RTL. We can use like many language programmer, many language programming. We can see that like I can see here Verilog or VHDL or HDL. So we can use this programming language to make a RTL. And then after we make this RTL, and then we can deliver to some software. It's like Cadence or Momentum or another software platform to make a layout. So after we make a make we write a programming language in Verilog or VHDL and HDL about our IC design, and then we can transfer it to layout. So in the digital IC, we don't need to draw our layout by ourselves, but some software, some dedicated software for IC design can transfer from our coding to the layout. And then after the layout is success, we have to measure, or we have to simulate the performance of the layout, and then we can fabricate. And then after fabricate, so we can see this is the wafer. After we fabricate, we make in the chip, small single chip, and then we can integrate in with another chip to get a system like this. So you can see from this picture that we have many chip. It is the chip, 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 chip. So we integrate in our system with many chip, and the chip have their own have yeah, different purpose or different function. It's like we develop a CPU, so we need many IC in our CPU. Okay, so how to design the IC? IC is mostly coding. So this is for digital IC, yeah. And then okay, we can only we can use the C programs, and then we transfer to HDL, hardware description language, and then we can design our IC. But for the analog for analog IC, it's like in my experience, we don't need to coding. We don't need to to master the coding in HDL, because in the analog we have the first one, we have to draw a schematic. So this is the from the analog IC. We have to draw the schematic, and then after that we have to draw the layout by ourselves. It's like if you see the PCB design, it's like it's similar to the analog IC design. The first we have to draw a schematic, and then after that we have to make a layout, or we have to place our component, and then we have to connect one component to another component in the layout, and then after that we fabricate, and then we can get the IC. So this is for analog IC. Okay, so the rest of this explanation is about the analog signal. So maybe I skip this one, and this is also the because I think you have learned about the digital signal in previous course. Okay, this is the signal type. So this is the analog, and this is the digital. Okay, so how to represent analog in digital? We can using the 1 and 0. 1 is high, and 0 is low. So it's like this one. It's like this is okay, analog signal, and also this is the digital signal. And then how to convert from digital to analog? We can use the DAC, digital to analog converter, and from the analog to digital we use the ADC, analog to digital converter. Okay, so this is DAC, then this is the ADC from the analog to digital converter, and then this is the one example for the ADC. So we can see that many from in one chip, many function. We have the comparator, the AC, ladder, encoder, demux, clock driver, and so on. Okay, and after this one is the introduction to circuit theory. I also know that maybe you have learned in a basic of physics about this one. So this is the Kirchhoff law, and then these are different directions you can write by yourself. So and then this is the KCL, Kirchhoff current law. Okay, just for refresh your basic physics, electrical physics. Okay, so this is the AC. Okay, and this is the KVL, Kirchhoff voltage law. Okay, also have learn it in the basic physics. And then circuit element also in the physics you have you learn about the resistor, capacitor, inductor, and then what is the relationship between the voltage and current in resistor, and what is the characteristic of the current and voltage in capacitor. Okay, this parallel plate capacitors also you learn in physics and also inductor. Okay, so this is the okay. Yeah, I just skip this one. Okay, okay. For the Thevenin and Norton, I will deliver this material later. Okay, this is important for you to see the or to analyze the circuit. Okay, so it's also okay. I think this is the end of our introductions. Okay, um, thank you very much. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.